Okay, so last time I mentioned that we have a whole lot of transitions that can happen. And in the end, when we get to room temperature, our iron is going to be some mixture of cementite and ferrite. But how that cementite and ferrite arranges itself is going to be very, very important to us. It's going to change the properties of our metal drastically. So the first one is, right over here, we have austenite. And this is just, different grains of austenite because we're above 727 degrees Celsius. And so it's stable above that temperature. And we've kept it there for long enough that it finally got to austenite out of liquid. If we begin to cool it below 727 degrees Celsius, then at those grain boundaries, we're going to have these structures begin to form. You can see these alternating layers of ferrite and cementite. This is what's called a laminar structure. Laminar talking about layers. And they're going to grow from the grain boundaries, and they're going to go from there. Now, what is happening here? Well, in the austenite, the carbon and the iron are pretty much equally mixed. But when I begin to cool them, I go below 727 degrees Celsius, it's no longer stable, and the carbon is going to start diffusing to one section where it begins to form cementite, and the iron is going to begin to fuse to the other ones. It's going to be trying to go to like things. The iron will stay in one place, the carbon will diffuse to another one. Now, as I change my subcooling, I'm going to have a different amount of perlite each time. So right here, this is saying how much perlite has been transformed. So how much is my austenite transformed into this perlite? Perlite is this repeating structure of ferrite and cementite. And so the larger my subcooling, well, the faster this is going to happen. It can happen in a second, it can happen in 10 seconds, 100 seconds, just depending on how much subcooling I have. As a note, this is not saying I have 600 degrees Celsius of subcooling. That's saying that I'm at 600 degrees Celsius. So it's 127 degrees of subcooling. Okay. So at high temperatures, so I kept it at a very high temperature just below the point where it begins transitioning from austenite to cementite, I'm going to have what's called coarse perlite. Now, why is that? Well, coarse perlite is when I have very large sections of ferrite, and then I have the cementite in between those. And I get that when I have very little subcooling because my iron and my carbon have plenty of time to diffuse to where they want to go. And so these ferrite layers get very, very thick, and the cementite layers are just matching them along the way. However, if I have a lot of subcooling, I will have very, very thin layers, very, very thin layers. Where I have cementite in between, and I have, just this little bit of ferrite there. Now, with that, what's going to happen? Well, if I have very thick layers, what you need to realize is that ferrite is very flexible. It wants to bend. Cementite, like its name, is very, very hard. It does not want to bend. So if I have very, very thick layers of ferrite, you can think of that as like a big cushion. The metal is happy to bend, and so it's actually very flexible and soft. If I have very, very thin layers of ferrite, because I cooled it very quickly, it's actually relatively hard. And the reason for that is because it can't bend as much. It's the same as if I take a whole jar of Play-Doh. Here's my Play-Doh right here, Kids love this. And I say, okay, let's take 2 plates. I put a bunch of Play-Doh in between. Well, I could bend this pretty easily. It's like a big Play-Doh sandwich. Now, if I were to take a bunch of plates, though, and put just a little bit of Play-Doh each time, what you would see is that even though the Play-Doh is still all there, I wouldn't be able to bend that because those plates are so stiff and they're surrounding it. It's not thick enough to actually do anything. And the thicker that I had the Play-Doh in there, the easier it would be to bend. So very similar for us. Okay, so this is what's called a time temperature transformation diagram. Here's my temperature. Above 727, I'm austenite. Below that, I'm not because austenite is no longer stable. After a certain amount of time, I will have a certain amount of transformation. Those curved lines are saying how much transformation I have. You're like, why does it only show the top? Because the bottom is something different, which we'll get to eventually. But the top is perlite. And so if I pick a particular temperature, in this case 675 degrees Celsius, and I stay there, well, after a certain amount of time, I'll be able to see that, well, I'm going to be just beginning to transition, then I'm going to be 50% transitioned, and finally 100% transitioned. Okay? And this actually matches up. So at this point, right here, I'm at that temperature. I've been there for roughly 11 seconds. And at that point, I'm going to just begin to transition from austenite to perlite. And then there, about 100 seconds later, I'm going to be at 50%, and then finally at 100% perlite. So these diagrams are very, very helpful. If I had a different amount of subcooling, so a different temperature I held it at, well, the amount of time would be different. So you can see if I go to lower amounts of subcooling, well, this process happens much sooner. And if I have just barely underneath 727, it's going to take a very, very long time. Okay. So we're going to say that we have a eutectoid composition. By that, we simply mean that we have the perfect amount of carbon in there. So we don't have, like, perlite and cementite, just extra cementite being mixed in there. We have this right amount for this transition. So we're going to cool it fairly quickly to 625 degrees Celsius, then hold it constant at that temperature. And that's why I've just drawn right there. This is my nice little isothermal process. And so from that, I could figure out when it's going to transition. So right at that 0% point, I still have all this austenite. Remember, austenite is a solid. It's not a liquid. It's a solid. It's just unstable below these temperatures, and it has to transition from Fe-Cementite cubic to Bi-Cementite cubic. It's going to do that along those grain boundaries. Those are the weakest points. That's where it's easiest for atoms to diffuse and easiest for us to have this transition. And so as I cool it, I'll begin to form this laminar or repeating structure of cementite layers and ferrite layers, repeating it over and over and over again, until finally I'm 100% transformed and I have everything being perlite. So this is it for this time. Hopefully it helps you to see how we're going to begin to look at how we cool things and how we cool things and how quickly we cool things, how it changes the properties of materials. And also we just began to scratch the surface of understanding why it matters how quickly we cool it, because in this case we learned that if we cool it really quickly, we have lots of very, very thin layers, and so it's going to be very hard but not very flexible. If we cool it very slowly, we'll have very, very thick ferrite layers, which allows it to bend as much as it needs to, and so it's relatively soft and flexible. So thank you so much. I'll see you all next time. Bye-bye.